I'm super excited to welcome Henry Fuchs today to give our first distinguished Reality Lab lecture of this year. There's honestly no better person to give this first lecture because Henry is a pioneer in VR and computer graphics. He's a Federico Gil Distinguished Professor of Computer Science at the University of North Carolina, Chapel Hill. Have been active in computer graphics since the 70s. First professor job was at 75, I believe. Is this true? 1975, which is amazing. A pioneer in VR and computer graphics rendering, high performance graphics hardware, virtual reality telepresence and medical applications and so on. Member of the National Academy of Engineering, fellow of the American Academy of Arts and Sciences, recipient of numerous awards, and even an honorary doctorate from TU Vienna. That's cool. So I'm really excited to have you here today, Henry. I mentioned you're going to talk, sounds like you're going to talk about next-gen AR glasses. Can't wait to hear about that. Thank you for doing it virtually as well. Welcome.
Thank you, Ira. It's so exciting to be here. I want to thank you all for inviting me. I've been meaning to come for a couple of years, but there was always something that came up during your spring speaker series, and there was no excuse this year, right? It's like, where am I going to go? Right. So thank you all for coming. Let me see if I could start sharing my screen. I first was going to talk to you about next-gen AR glasses, but as I was thinking about this, especially for students, I realized that I may be missing an opportunity to tell you about some history. And so if you'll be all right with me, especially those of you who've been in this field for a while, I want to talk to the students about some history. I'll talk about next-gen AR glasses for 20 minutes or whatever. But there's some really interesting history, and it's about to pass us. So here is what I have in mind to tell you about. I want to tell you about the historical background that got me interested in this, which was Sutherland's 1968 system. I want to say a few things about the kind of work that our group does, just so you don't think it's nothing but AR glasses. Then I'll talk about today's topic, and I want to talk to the students especially about what I see are a few of the interesting opportunities, okay? So let me tell you, when people talk about the origins of VR, they often say it's Morton Heilig and Sensorama from the late 50s and early 60s. And while that's true that, as far as I know, this is only from secondary information, that he could record stereo images in sound and put in vibrations and smells so you could get a feeling of immersion of riding a motorcycle. And then he later had the idea that you could wear a couple of TV sets on your head. What I think was missing here was what we think of as VR and AR. That is, you could move around, you get head motion parallax, you get head tracking, you get interaction, you have a 3D world. And all of that came all at once in 1968. It's hard for me to describe to you guys, again, I'm talking to you as the students, how much of a shock this was when I heard about this system in 1969 from Alan Kay. Because at the time, I got interested in this because I had a summer job at Jet Propulsion Lab's image processing lab. So for those of you that don't know, JPL was then in charge, continues to be in charge of the unmanned deep space probes. And at that time, the thing that was happening that was really exciting was mapping the moon's surface for the coming astronauts. And so there were streams of images coming down from the lunar orbiter, and we were processing it. And I, as a summer student, got to do not just that stuff, but all kinds of other crazy applications that had to do with image processing. You know, how do you recognize houses from aerial photographs? Or how do you recognize monoclonal antibodies? Or how do you do chromosome analysis? You know, in the state-of-the-art image processing lab. I'm looking at some students, but I don't know any of you students. I know all the professors, okay? Somebody who's a student nod, okay? You understand this? Now, let me tell you what the state-of-the-art was when I read this paper in 1969, 1970, okay? There was, in the state-of-the-art image processing lab at JPL, I don't remember a single graphics display. Is that clear? There was no such a thing as a frame buffer, okay? What we had was a really fast IBM 36044, and we had a bunch of punch cards, and we had some special image processing libraries, okay? And you say, how would you do image processing on that? I'll tell you. I happen to take one of these things out. Can you all see this? Okay. This is how we did image processing. Okay, so we ran our programs on a fast 360. We told the program beforehand that we wanted certain images mounted on 9-track tapes. And then we processed them, and then we wrote out the images onto another 9-track tape. Is that clear? And then some poor fellow, no, not poor fellow, a technician would take off this tape that had images recorded on it, of course in binary. He would take it into the next room, in which there was a dedicated tiny computer which read the images from the tape and scanned out on a very expensive flying spot scanner and exposed this film. This actual film it exposed, okay? And then that guy, when he had a whole bunch of these, okay, exposed, like 100 images, he would take them into the lab next door and he would develop them in chemicals. And then after developing them, you know, hang them up for a half hour, and then he would print them with an enlarger on 8x10 black and white, okay? And while they were still wet, he would put them in between paper towels and he would deliver them to the people involved. You understand? This was the state-of-the-art image processing lab. And so I still remember fondly, I felt so great here during the day. These images, 8x10 glossies, would appear on your desk. You get the picture? Now, I read this paper that Alan Kay showed me. It was then at Stanford. I took an independent study. And he says, here is this thing that you put on your head and you walk around and it shows you images in front of you as if they're in the same room with you, right in front of you. You could walk around it. It blew my mind, okay? It had a stereo display, see-through augmented reality. So you still saw your hand, you saw the device you were tracking with, okay? It had real-time stereo image generation with perspective, okay? And very low latency. I didn't even know what latency was, okay? It had head tracking, not one, but 2 different 6-degree freedom head trackers. By the way, do you see this image? I'm looking at the students, okay? So people say, oh, this is Sutherland's Sword of Damocles system. The Sword of Damocles was Sutherland's affectionate name for just the backup mechanical tracker. The first tracker you could see here. Notice this thing here is not connected at the bottom. You all see that? That's because in 1968 at Harvard, they had the first of the trackers and had ultrasonic transmitters here, 3 of them here, and ultrasonic microphones, 4 of them here. And simultaneously, these would send out pulses, each at a different frequency. These microphones receive 3 signals all simultaneously and would determine the latency between when it was sent and when it was received. And using those 12 numbers, figure out the pose of the head mount. You understand? Totally tetherless. Okay? It turns out, according to Ivan, it sometimes glitched. And the reason he said it glitched was that there was a heater back here. And during the winter, when the heater would be on, it was gas and there was forced air with a fan. And then the temperature on top of the room would change drastically. And the time that it took from the transmitter to receiver is a function of the temperature, and it glitched. And so they built this backup mechanical tracker, which had a sliding arm here and had 2 shaft encoders here and 2 shaft encoders on top. And that's what was at Utah when I arrived there in 1970. So you will know now that this sort of Damocles is not the name for the whole system, but just for the backup mechanical tracker. And some people think, oh, it's because it weighed so much, you know, you needed something like spring loaded. No, of course, it hardly weighed anything. You could see the thing here. It was perfectly fine. It didn't weigh much at all. Is that clear? So now you know. And when I see Ivan, I say, can't somebody correct this? This is totally untrue. And he nods. He said, yep, somebody should correct this. But of course, you know, he has better things to do with his time. Okay? So here's the only thing that I've ever found of video of this. This is in fact already at Utah. Don Vickers, PhD student before me. And you could see, in fact, you see it's white on black rather than black on white as it is in the paper. Okay, it's the thing that got me into VR. And by the way, if you're interested in more of this, 2 years ago at SIGGRAPH, there was a VR at 50 celebration, and Sutherland and Bob Sproul and Chuck Seitz and Quinn Foster all talked about the system that was then 50 years old. And Fred Brooks, who many of you know is a pioneer of graphics in his own right, gave the introduction of what the state of the art in graphics was in 1967 before this system was built. Okay, so that's the background in history. Before I say a few things that our group does, I want to mention that there are lots of people who are currently or have been recently at UNC who've done lots and lots of work in VR and AR related fields. And I don't have time to talk to you about their wonderful work, like Fred Brooks, Dinesh Minocha, Ming Lin, and Selma Lastra, and many others. And I'm just going to tell you about a few of the things that we do so you don't think that we just do AR glasses. So we've been doing model construction. Boy, did ERA say I've been doing this since '75. This was my dissertation on a 3D scanner. You might be able to tell that this is a human being, one of my friends who's lying down, and I scanned this person. But you probably cannot tell the gender of this person, right? I assure you that you could tell the gender if you would see her. This was crude, so crude that you could barely tell it's a human being. But that led to work on how to do optimum reconstruction from surface contours. And we've been working on 3D reconstruction of scenes for a long time. And I'll talk in a few minutes about what we're doing for AR glasses. We've also have been doing image generation, as Ira had mentioned. We built graphic systems that were the forerunners of GPUs with, you know, a mere 2,000 chips in some of them. We've built, you know, algorithms to be able to do things rapidly. We occasionally build algorithms that will project onto weird surfaces like this dollhouse that my daughter is painting, and we're doing some stuff in holographic image generation now. I think the biggest problem in head mounts is the head mount itself. If you ask me what's the biggest problem in AR displays, it's AR displays. They're not good enough. They're getting there. I mean, the Magic Leap is much better than the thing that was, 3 or 4 years ago. The HoloLens, I think, is very nice. HoloLens 2 is even better than HoloLens 1. So I think they're getting there. Question is, will they ever get there? Okay? Get there in the sense that we're willing to wear them when we don't have to wear them. Okay? That we're willing to wear them during the day to do everyday things. Nobody forces me to carry my mobile phone around, but I carry it because it's so useful. And so we've been building head mounts for a long time. We're still building them because we think it's so important. We've also, the second most important problem is you need to do tracking really well. And we've been building trackers for a long time. Our latest one appeared last year in TVCG 2019. So this is one that goes at 50 kilohertz or something like that, because we think we need much better hit trackers. And we're really into integrating all these technologies into an application and trying them for real. And so we try them. So here's one or two examples. This is one of our early systems from like 25 years ago. This is Etta Paisano, then head of breast imaging at UNC, who is examining one of her patients with a suspected breast tumor. And this is early on, I'm sorry, 25-year-old videos, I can't find the right ones. This is very early on in the procedure because, of course, when she's actually doing the procedure, she is injected local anesthetic, and then she's, she has, all kinds of gloves and so on. But you might be able to get some idea. She's just trying to get a good feel for where the suspected target is, and it's right here. And so she puts her finger there, that's where she wants to inject local anesthetic. So we do other work like record entire surgical procedures for training, and we do some work in laparoscopy and force feedback with people at the University of Arizona. So the topic at hand. The topic I really want to talk to you about is augmented reality eyeglasses. And the reason I chose to talk to you about that is that I think that they're the things that are going to change the world, so to speak. And I think that they'll be like mobile phones in the sense that they will be, I believe, widely daily useful for all of us. But just like mobile phones are much more than telephones, I think AR eyeglasses would be much more than just AR displays. And that's what I'm hoping to convince you of, is that there is a bright future, if we could just get there, of having lots and lots of capabilities in AR eyeglasses. And let me tell you what I mean by it, okay? Of course, people say that we could have see-through displays. Magic Leap 1, HoloLens 1 and 2 are that, okay? But what other things may we want, okay? What we want, it seems to me, is just like mobile phones, we'll stuff these with all kinds of sensors, with cameras, with IMUs, with lots of other sensors, because they'll prove to be useful. And they'll do several things. I think that they'll reconstruct their 3D surroundings because it'll be really useful to do that, okay? They'll be able to reconstruct the viewer's body and face because it will be used for the user, for the system to know the user's pose and where the user is pointing and what the face is. And that reconstruction will help also in a lot of applications. And the personal assistant that will be in these glasses, I think, will be much more useful as a result. So for example, right now, when I say something to Siri, and I say, how much does this thing cost? I have to point the thing that I'm interested in, I point the camera to it. Or if I'm at a certain place and my hands are full, I cannot do that because my hands are full, right? So I think that once we have them in eyeglasses, we'll have these be a lot more useful, okay? So let's start with a simple example. We were thinking about this because our lab manager, we wondered about if he ever gets sick, we're in deep trouble. Okay, so suppose that he were sick and he's recuperating in a hospital, and now we're having trouble with our latest 3D printer because we don't understand it as well as he does. We don't want to use the standard Zoom application because then we have to go take it to our lab, and he's not so much aware of it because think about what Zoom and all the other things do. You are at the mercy of the camera that's here, right? You don't want to be at the mercy of that because you might be interested in something that I'm not pointing my camera to. So for example, if we point this thing over here and you are interested in some particular book or the painting that I have in the corner, if you were here with me, you could of course do that without asking me. But now you're at the mercy of my moving the camera. Is that clear? We don't want to have that. And once we liberate ourselves from being at the mercy of the camera, my feeling is there'll be no going back. Okay, but we have to get that capability to be able to liberate ourselves. And this is true in many, many applications. Okay, so in this case here, let me see if I can put it here. It may be that we think that the problem is here with the printing head being stuck. But the expert may realize that it's the material that's being fed that's the problem. You understand? So I've discussed this at various times with various experts. For example, we were interested in doing telepresence for the military once, and we had some funding. And I talked to my closest colleague, who's allegedly the best surgeon in the area. So I said, Tony, you think we could do that? You know, do this telepresence, you know, with telesurgery. He says, nah, that's not the problem. He says, the problem is not teaching somebody how to do suturing. You could teach a core man, a core woman how to do that. The difficulty is how to get situational awareness of what the most likely source of the trouble is. Is that clear? And so he says that lots of times in telemedicine, the people in the field are pointing at the wrong thing. They're pointing at what they think is the problem, but the person remote realizes that there may be other things that are more serious. Is that clear? And once we liberate ourselves from the camera, then the expert could look around. Is that clear? Do you have any questions on that? Okay, so now there's been great telepresence systems done. In fact, if I would have been up with it, I should have used an example from what you guys do because you guys do such great work. Okay, but here's one that I happen to have some familiarity with, you know, Microsoft Research, their holoportation system. It's really great. The only difficulty is that if you look at something like this, you say, well, holoportation depends on having a couple of dozen cameras all around the room. And we're not going to have a couple of dozen cameras around this part of the lab because who knows? Half hour later or 10 minutes later, we want to go to another part of the lab. So the disadvantage, in my view, in current telepresence systems is the multiple cameras that need to be deployed in order to do that reconstruction. Okay, so here is what we think the solution is. Of course, we haven't gotten there. This is sort of like saying, we think the solution to commuting is for everybody to have a helicopter. Just because you propose it doesn't mean that it's the right solution, okay? But here is what we think. We think we put everything that we need into your glasses. And that way, you always have it with you. So our first attempt at this was to take a HoloLens 1, and just put a bunch of cheap cameras all around it. Okay, 4 of them looking outward to reconstruct the environment, 2 of them downward to reconstruct the body, 2 of them inward to reconstruct the face. Is that clear? Now, of course, the problem is that you really cannot do that well because you get a terrible view of everything. And so what you need to do is use the power of neural networks to train them so that if you train them with lots of data, that they could give you some hint about where the various joints are in the body, even when you get very lousy looking images like these. Okay? So now, once you train them, then you get some hint of where the various joints are. You could put those joints together into your skeleton, then deform your body model to the current reconstruction of the skeleton, and then move that body. And right now, we just use state-of-the-art methods like structures from motion to reconstruct the 3D environment. Is that clear? So let me give you a little bit of this. Now, I warn you, the audio is terrible in this because I didn't realize until we actually did this that there's a lot of street noise. The process. All right, so let me set this up for you. Here is Connie Liu, a first-year PhD student, and she has the HoloLens and a bunch of these cheap cameras. Is that clear? Nothing else. Somebody with a mobile phone is recording this, so you could see nothing else happening here. Okay? And then what these things do is we send this back via Wi-Fi to the lab. We reconstruct the 3D environment. Then we reconstruct the body in the way that I described to you. And then we send all that to Nick Rakowski, who's in the lab and who's walking around with a standard head mount. I think HTC Vive, if I recall correctly. So now when she's walking around here, you are not, Nick is not slave to her cameras. Is that clear to you, students? Okay, he can walk around wherever he wants. Now, of course, he's going to look around and the reconstruction when parts of the scene are far away from the cameras is going to be lousy. But of course, we may get better later. So listen to this. I'm sorry, there's a lot of street noise.
You can see the historic Carolina Inn Hotel. Department members sometimes hold lunch events and meetings in its restaurants. Down the street are the expensive UNC medical facilities and hospitals. In the opposite direction, we reach the center of Chapel Hill's downtown, with Franklin Street and its many shops and restaurants. Well, this is the...
Okay, so you get the idea. It's very primitive, but what I hope you get is that there's nothing else but what she's wearing on her head, and that you're liberated from the camera. You could walk around anywhere you want. And you could see how, easily see how this could be generalized to lots of things. That is, there is Google Earth. You could integrate this with Google Earth. You could integrate this if there's other people who are willing to share their information with you. So there's lots of ways that you could make this better. Okay? So let me just tell you some obvious things. Legs are almost impossible because we just don't see anything of the legs most of the time. We occasionally see a leg, you know, when it's stepping forward, but when it's stepping back, there's no hope. So we just hallucinated legs as she moved around, okay? But given that you could buy standard shoes which have IMUs in them, what one of the students is working on, Young Wu Chow, is using those IMUs if you have them, or if you have IMUs on your wrist. Let me mention one or two other applications while I still have the time. I think virtual personal assistants are going to be much more useful when they're aware of where you are and what you're looking. So here, this is one of our first test cases. This is, in fact, right outside our lab. And what we like is not just that the assistant is aware of you, but that you are aware of where the assistant is. So in this case, you ask the assistant how to get to Henry's office, and it's not just that the assistant will tell you, the assistant will lead you. So let me play a little.
Henry's office.
Can you hear that?
We will first turn left at robotics lab. Follow me. Would you like to know more about this poster?
Yes.
This poster says that it is located in Chapel Hill. Would you like to know more about Chapel Hill?
Yes.
You're probably not interested in Chapel Hill right now, but you get the idea.
Office.
Okay. So
we will turn left at robotics lab. Follow me.
This is inspired by Eve in the movie WALL-E, so it's a friendly assistant. And let's see if I can speak.
Turn left here.
All right. This is actually takes real time. How long it takes you to get to my office? Let's see if we could. Oh, here.
Would you like to go somewhere else?
Take me to the reading room.
We will follow me.
Okay, you get the idea. Okay,
Henry.
so.
Sorry, this is Steve Seitz.
Steve, thank you for asking a question or a comment, Steve.
I was just wondering whether this brings back fond memories of your office.
I hadn't thought about that, but yes, it does. I haven't been in my office in several weeks. Have you been in your office in several weeks?
Yes, I have, but I know the feeling.
All right.
Mark, you can go ahead and ask your question.
Yeah, so in terms of years, how far do you think we are from non-dorky AR glasses, or just AR glasses that the average person would be willing to just wear around in public?
The safe answer is 5 to 7 years.
5 to 7?
But that's because, you know, a lot of things can happen in that. My guess is that there will be some that are a couple of years out, but they won't have all this function. And as a result, they won't be so widely useful, right? So it's sort of like saying, when will the first mobile phones be here? Well, we had mobile phones the size of a shoe, but they weren't the kind of mobile phones that we know and love today. So I think within 10 years, I think they'll be in widespread use with these kinds of capabilities. And the reason is that the jump from utility of laptops to mobile phones was so great that I think many people feel that there'll be a similar jump from mobile phones to eyeglasses. That when it's with you all the time and when they knows a lot more about you, it will be a lot more useful.
And how do you think the ARs will do their computation? Will it send information to some kind of cloud?
Oh, I'm so glad you asked. I have that as one of my points on the next slide. Actually, 2 slides. Okay. Yes, absolutely. I think that's so. Let me mention 1 or 2 more things before we get to that. I think autofocus might be, in fact, the most useful thing. And autofocus has to do with not just autofocus for the eyeglasses, but autofocus for virtual objects also. Okay. This is commonly called accommodation. So you probably cover this in your VR class, right? So here is the problem. This is David Dunn's conceptual drawing. Here you are, say, with your eyeglasses on, your AR eyeglasses, and you're looking at this guidebook, and you're walking down the street. Are you with me? Now, the physical guidebook is here in front of you. You see my cursor, right? And the physical street is in front of you. And there are simple labels like you mark something in the guidebook that was an interesting place. And somebody else, you know, your best friend mentioned something in the guidebook that was an interesting place. And these have corresponding things that look interesting out here in the real world, right? We all know that when we focus close by, it's a different focal cue than when we're focusing far away, right? But most systems, in fact, including Magically One, only have one or two choices about the display distance. And that means that when we're looking at close by, or when we're looking at something far away, the internal display of the AR glasses may not match the proper distance. So I'm looking at you students. Is that clear? All right. So there are a number of different solutions to this all throughout the literature. Here is one that we've been working on with friends of ours at NVIDIA and friends of ours at the NPI Informatics and friends of ours in Switzerland. Here, it's a very simple idea. We just take the half-silvered mirror that normally will reflect what's in the internal screen into the eye, and will pass the visuals from the real world to the eye, and we make it curved. Think about this as a rubberized sheet of mylar. And with some air pressure, we could have it curved at different distances so that the internal display appears at different distances under computer control. What that means is that we could make the virtual display be anything that we're interested in. Is that clear? And we have to know where the person is looking, so we need some eye tracking and other ways by versions to tell where the person is looking. But it turns out that if you use some liquid lenses here, then you could tune this so that it changes the focal depth of what you're looking at, which for older people like me is really useful, because otherwise what I need to do is wear multiple glasses or tilt my head when I have bifocals. Is that clear? So now the trick is that for the external world, you have this tunable lens. For the internal display, you have a combination of the lens and this deformable membrane. And if you just calibrate it properly, then it turns out you could get independently the real world and the virtual display both in focus. Pretty simple idea, right? And so here's what happens for an older user whose natural focus is at 7 meters. Basically, nothing in the lab is in focus and nothing on the display is in focus, okay? But with the AR adjustments, we make it so that he could see both the bunny here in focus. You can in fact see the individual pixels here, and the textbook at 1 meter, both of them in focus. Okay, so this appeared at 2018 in ISMAR, work of Praneeth Chakravartula and David Dunn, Kanakshut. Let me tell you one last thing before I think that virtual personal assistants are going to be really useful for lots of things like physical therapy. This is a very personal thing with me because I had some problems with my leg a couple of months ago, and I needed to go to physical therapy. And I could tell you that my physical therapist corrects me when I'm not doing things properly, even though I have a video to assist me. And so by having your built-in personal assistant that can pay attention to you, it could pay attention when you are at the therapist, and when you're at home exercising, it could say, wait, something that you did here, but I happen to reconstruct your body is at a different angle when you did the same sequence of moves when you were with a physical therapist. Okay, so Mark Miguel, you were asking about eyeglass display. So here's my next to the last slide. There is a lot of really interesting problems to work on because a lot of problems need to be solved before this kind of a system will be useful. First is the display itself needs to be in an eyeglass form factor, and it needs to have a wide enough field of view so that it's comparable to our eyeglasses. Current systems, as you well know, take different approaches to this. Some of them make the whole thing narrow so that you feel like you're looking through Coke bottles. Others make the physical display wide, but the virtual inset is small. And that gives you the illusion that the virtual world disappears unexpectedly as you look off to the side. Okay, I think holographic optics is the most promising technology, and I invite you to look at Praneeth Chakravarty's paper in SIGGRAPH Asia last year for some indications of how to make those really good. Then is, I guess, Mark Miguel's question, how are you going to do computing on these eyeglasses? I think is an enormous problem because we cannot have anywhere near the power that we have in current devices. People are just not willing to wear something that is the size of Magic Leap 1 or HoloLens 2, in my view. They will wear it for professional reasons. If they're an architect, or if they're a pipe fitter, or if they're a surgeon, they'll wear it during that time. But that's not where the most changes will be in society. In my view, changes will be when everybody wears it. So what is needed is much, much lower power. And what that means is basically distributed computing. And that means we need to rethink the entire rendering pipeline for not just low power, but it needs to have really low latency. So here is work from Peter Lincoln from 2017. So here is his really low latency system, which is 80 microseconds from head mount motion to the new image. And here is what happens when he injects standard 16 milliseconds, 1/60th of a second latency. If you just look back and forth, you will see that the synthetic image of these teapots here, you notice how they appear to like swim on top of that real desk. They don't swim if the latency is down at 80 microseconds, but they do swim when it's at like 16 milliseconds. And by the way, this rotation at 25 degrees per second is pretty slow. It's much slower than we measure when we are following a conversation between two people in front of us. So we need not only low power, but low latency. And the tracking subsystem needs to be much better, not just tracking the eyeglasses at very low power and low latency, but we really need eye tracking that's much better, because we need eye tracking for rendering efficiency. You probably all have heard about rendering efficiencies that are gained by looking at where the person is looking. And there's also, it turns out, all kinds of concerns that the eye box, that how you wear your eyeglasses might be such that if you wear them slightly askew, then you will not see the whole image, especially for holographic optics. And you need to track the eye really precisely to know how you're wearing the eyeglasses. Finally, I think that the applications and user interaction is so unknown that we have hardly a clue about how people will use these. And the only hope, I think, is to try these early applications with real users. So I could tell you, for example, in working on how to do augmented reality guided needle breast biopsy that it took us years of work and many mistakes before we got to this point where real patients were treated by real physicians. But in my view, it was worth the effort because we learned an enormous amount. So I want to thank all these people who actually do the work. I get to come talk to you. We're blessed with collaborators in a number of places, in Shanghai, in Singapore, Facebook, some people here, at NVIDIA, at MPI, and in Switzerland. And I forgot a few of them here, and I forgot because I didn't talk about the work that we do in collaboration with them, like people in University of Arizona and University of Florida and at other places. So with that, I thank you for paying attention and putting up with machine application crashing. And I thank you for having me here.
All right.
Thank you. And thank you for having me.
Yeah, thank you so much, Henry. Do people have questions? Feel free to. Michael Cohen just wrote, thank you, Henry. Michael, are you there? Feel free to ask questions at this point. We have time. Looks like Dylan, are you raising your hand? No. James, yeah, go ahead.
Hi, this is more of a personal question. When I first started getting interested in AR and VR, I learned of a gentleman named Steve Mann. I think he was from MIT. And I was just wondering if you have come across him during your time working, or because I believe that some of his projects were like the precursor for the Google Glasses, if I'm correct.
Yes, we have met at some conferences. In fact, we had a conversation, I think, in one of the airport gates while we were waiting for the same flight 1 year after a conference. We have never worked together. I think it's really interesting that he's worn his headgear, as I understand it, for a really long time. And I think that's a really useful thing to try. I'm not quite that brave. We wear our things, but not for that length of time.
Yeah, I was always very intrigued by his idea and enthusiasm for wearable computing.
Yeah,
so,
I think it's great too. One of the things that we try to do is to try to get feedback, not just from our group and the people who are developing it, but also from the users that are that we're intending to make them for. Because sometimes what we learn is that our assumptions about what would help them are wrong. I mean, there's so many examples of laparoscopic surgery. I showed you a little picture of this, but didn't talk about this. You know, laparoscopic surgery is called keyhole surgery because you're just looking with a little laparoscopic camera into this abdominal cavity, and you're doing this with sticks, you know, manipulation. And I naively thought, you know, if we could only reconstruct the 3D environment, then we could make the patient appear like their abdomen is totally transparent, right? And then you could like see through it. It's like open surgery. And I don't know, the second meeting we had was laparoscopic surgeons. One of them said, Meredith Duke, she said, oh, you know, can't you just, I don't want to see it right where the actual patient is. Can't I just move it up to where I could see it comfortable eye level? Can't you just do that? Of course, here, how high would you like it? But none of us even thought about such simple things. So there's a lot of things to be learned. So this is a long answer to your short question. I think it's really great to try your own systems, but it's also very useful to have other people try them for whom you're building them.
Absolutely. Thank you very much.
You're welcome.
Natalia, go ahead.
Hi, you were talking about 8 cameras and you said 2 for the body. I'm just curious, where the two cameras for the body are located? Like the two in
They're
front?
currently located right on the corners of the glasses looking down.
Okay.
So they're as far out as we can make them and still be attached to the camera. But if you could think of something better, we'll put them someplace else.
I'm just curious, how do you know how the back of a person, like?
Oh, in fact, we don't. We don't.
Oh.
What we do is in the last year's system, we assumed that somehow somebody has seen that person before. And so, you know, we assume that this person is wearing the system for weeks and weeks on end. And so they have somehow gotten some notion of their back.
Okay.
And in the future, what we hope is that the system will recognize their clothes. So we have some colleagues who are specializing in recognizing clothes. And what we hope is that in the future, the system will recognize your clothes, because at least I have a limited wardrobe. And if it sees the front of my shirt, it has a pretty good idea of what the back of the shirt looks like.
Yeah.
We're also working on how to collaborate in reconstructing this. That is, if sometime you're wearing your glasses and you're talking to somebody else, they have their cameras have a better view of you than your own cameras. And so they will get an idea of what you're wearing, and they may in fact see your back system.
Also another question.
Sure.
So the cameras are just regular like webcams? They don't have like a basic...
They're cheaper than webcams. I mean, we try, yeah, so we used a number of, you know, we use point and gray cameras, we use Toshiba cameras, we use, in fact, some of my favorites are Autofocus. Autofocus has some really great cameras for like $25, $30.
Oh, that's pretty cool.
Yeah, I highly recommend them.
Thank you.
You're welcome.
This gives me an idea, Henry. What if you take, related to Natalia's question, what if you look with your cameras on a mirror back and forth? You'll be able to...
In fact, funny you should say that. Right. So Chao Zhang, yes. One of our students is working on that problem. Thank you, yes.
Cool.
Yes.
Abhinav.
Yeah, hi, Henry.
Hi.
So my dad works for telecom, and he talks about edge computing with like 5G and stuff like that. Do you think like the latency and the computing power is there for being able to connect AR glasses to the like a mobile network and do computations there and then relay the information back rather than doing it on there, and that would reduce the size theoretically?
Oh, absolutely. And I think what will happen is there'll be like 3 or 4 layers. Sort of like in a computer system, there are 3 or 4 layers of memory hierarchy, right? So I think what will likely happen is there'll be the very barest minimum in eyeglasses, hardly anything. And then there'll be something that it will depend on for the rest of the system using, you know, Bluetooth, say. And it will depend on your mobile phone, which you probably will have in your pocket because you don't need to take it out so often. And your mobile phone will do many of the computations, and your mobile phone will then use things in the cloud to do real heavy lifting. Yeah, so I think you're absolutely right that we need to have this hierarchy of processing capability in which you get more and more power the farther and farther you go from glasses.
Right. Cool. Thank you.
You have to rethink a lot of these problems. I mean, you know, think about even just tracking when you want to reconstruct the environment. Running 8 cameras is a lot, and all the algorithms that you want to run on them.
Let's see, Patrick, yeah.
Hi, Henry, thank you. So I thought the whole telepresence concept was really interesting. And I was curious to get your perspective on the privacy implications of telepresence.
I think that they are enormous. I think that they may be the big showstoppers. I worry about privacy in society. We had I was in a meeting this morning of our faculty in computer science and the provost, and we were talking about data and information in society. And I think that the COVID-19 experience is sobering in so many different ways, in privacy among them. Privacy among them. Yeah, I think it's, I could tell you that I think there's short-term solutions, you know, like say you don't need cameras to do this tracking. Okay, so we know that we could do tracking with other kinds of non-image sensors. You could look at papers by a lot of people, including ourselves, on, for example, lateral effect photodiodes. So these are diodes that have a whole area of sensitivity, and so they could do a lot more than just a single diode can. So they'll give you something like a centroid of the light that's hitting them, you know, through the lens. So they don't give you an image, but they give you something that you could train to do a lot of interesting things. So I think a lot of tracking could be done with that. And my guess is some of the privacy issues would be minified by using non-camera sensors for most of the tracking.
Awesome, thank you.
You're welcome. Well, seeing you next to Paul DeBevec is so amazing. It's like, you guys realize what a rich source of experts you have local to you. It's just amazing.
Thanks for the great talk, Henry. That was really fantastic.
Thank you, Paul. So nice to see you.
Let's see, last call for questions. If there are no other questions, then we'll finish. I don't see arms. Great. Yeah, so a last round of applause, and thank you so much, Henry. This was great.
Thank you for having me.
Yeah.
It's a pleasure to be here. And I look forward to seeing all of you in person when this thing is over.
Definitely, yes. Looking forward to that.
You all keep safe. Bye.
Bye. Everyone stay healthy.
Thank you.